All right, so this is radioactive decay. Um, this is here because basically they want you to know that mass can convert into energy. Okay, you almost never use this equation. What you do typically is you look at, here's a reaction, right? You've got the parent nucleus, maybe, right? And then you have the daughter nucleus plus the particle, right? And this is just a decay reaction, but if you look at the products of the reaction and the reactants or something like that, we can look at the mass, and if it loses mass, you have to say, where did that mass go, right? Well, it went into energy, right? And if it gained mass, you'd have to say, where did that mass come from? And of course, in that case, it couldn't be a decay. It would have to be like two particles colliding, and the energy would come from the kinetic energy of those particles. So that's what they're doing with the Large Hadron Colliders. They're taking two protons, right, that are just, their masses are totally dilated, so they're just fantastically much more massive than they would be at rest. They're colliding them and generating these very short-lived but massive particles that haven't existed in any great abundance since the Big Bang, right? So in that way, the superconducting supercollider is a time machine, right? We're creating short-lived massive particles from the kinetic energy of these little protons that are slamming together. Okay. So anyway, years ago, I had a student. He goes, "Yeah," he says, where did the mass come from? Where did it go? Where did it come from? Cotton Eye Joe. Anyway, sorry, that's a service I provide. But anyway, what you typically do is you're going to look at these masses, right? And it's going to be, mass final minus mass initial. And you're going to do this in AMUs and then multiply by 931.5 MeV per AMU. And this is the magic number, right? And if we've lost mass, if it's a negative thing, then we've given off energy. It's exoergic, and if we've gained mass, it's endoergic. It requires energy. Okay, so I think that's why that's there, right? And then we've got the nuclear decays, right? We've got alpha particles, beta minus, beta plus, gamma rays, right? Remember, this guy's just a photon. I think I didn't know this like my senior year of college. The guy was like, "Well, what is a gamma ray?" I'm like, "Well, I don't know. It's a thing. It's just a high energy photon, right? Ultraviolet can give you a sunburn. Gamma rays are used to sterilize meat. Okay, like they'll kill you, right? A beta plus is a positron. It's just an antimatter electron, right? An E plus, and then this is an electron, right? So in physics, we call electrons electrons. We call them beta minus. We call them cathode rays, right? That's kind of fun. And then an alpha particle is a helium nucleus, right? So it's two protons, two neutrons. It's a big boy. So massive, massive nuclei can become more stable by just literally shedding mass, right? And then let's see, a beta minus. If you create a beta minus, then you must gain a proton, right? Because you're literally creating an electron that hasn't existed before in the universe, right? So if you create a negative charge, you got to create a positive charge. Okay, so this would, I guess, make you less neutron rich because you'd turn a neutron into a proton. And then this guy, I think you're turning a proton into a neutron, right? Because this positive charge didn't exist before. So it has to come from, I guess, the positive charge of a proton. Proton turns to a neutron or something like that. And then the gamma ray just literally decreases the energy. So the nucleus has energy levels like the atom does, right? Only they're huge, and it can stabilize itself from a high energy level to a low energy level. You see these little energy diagrams like this, right? Okay, it can go here, it can go here, and then here. So there's all kinds of gamma rays that you can get for a particular, and these are usually after one of these guys. A particular radioactive decay can cause several of those, right? And then the rate of decay, this is the rate, right? So if we look at the graph, the end, we get this nice exponential. It doesn't quite reach zero, right? And notice this is the original amount. This is the decay probability, which you can get from the half-life here. Okay, and this is the elapsed time since when the number was this. Okay, now this is set up for the number of atoms. It also works for the grams of atoms. It also works for the activity. So let's say it's initially, 5, the activity is 50 counts per second or decays per second, right? You could just put that in there, and then, after how much time is it 25 decays per second? Well, that would be just one half-life, right? Okay, you don't have to do any other calculation. Anything that scales with the number of atoms, you can throw in here for the original and use it for that, right? So again, you can do grams, the original grams that you have, this is how much you have after a certain amount of time. The original activity, this is the activity after a certain amount. And certainly you can do it with the number of particles, right? E to the minus lambda t, that's this thing, right? Okay, and then this is the activity, which I hope you just see that what's in the parentheses, it's just that, right? Like, I don't know, did they think you're not clever? See, I don't know why they give you some formulas and then they don't give you other ones, right? But anyway, there it is, right? So the activity is literally the decay probability times n. So if you have a 1,000 atoms, if n equals 1,000, and your decay probability is 0.1. This is the same probability you learned in maths class, right? Okay, if it's 0.1, right? Well, the odds are, if you have 1,000 nuclei and each one has a 1 in 10 chance of decaying, in the first second you're going to have 100 decay, right? Chances are, right? Okay. Now with 1,000, you're going to have quite a bit of variation because it really is random. It's going to be this, bell-shaped curve. If you have a mole of atoms and the decay probability is 0.1, you're going to get exactly 0.1, of that will decay in that first second. Okay, so anyway, that's what's going on there, right? Okay, and then this is new. I love this. They added this. We needed this. Okay, it's the relationship. So this is the half-life. The half-life is typically, then nobody tells you the decay probability, right? Okay, they'll give you the half-life. Okay, now just a pro tip here. Okay, when you're doing this is the half-life. Let's say they give it to you in years. Do you have to turn it into seconds? Or could you figure out the decay probability per year? You can find the decay probability per year. Yes? So let's say the half-life is, 4.5 times 10 to the 9th years or something like that. That's our half-life, right? You can plug it in here and get the vanishingly small decay probability per year. Then you can plug that in there, right? And it's going to be probability per year. I don't know, probability is like a pure number, right? Okay, you can plug that in there. And then, of course, if you plug in the time in years, right, the exponent has to be a pure number, right? So it can't have units. And so if that's per year, and then you multiply by years, you're going to have a beautiful thing happen, right? And you could figure out, how much will be left after so many years if you want to. Of course, you can do everything in seconds if you want to. I'm just pointing that out. Okay, you could do per minute, right? You could do per second, right? Technically speaking, that lambda is supposed to be the per second or something, and t is supposed to be in seconds, but you don't have to do that, right? You can also do this, right? N is not 1/2 to the t over t 1/2. Is that right? That'll work, yeah. Because if you're 1 half-life, then it's going to be half, right? If you're 2 half-lives, you're going to be a quarter of it, right? You can do that. Anyway, yeah, there's lots of things you can do. I'll just stop talking.